Hello everyone, and welcome back to some more remote learning. In today's video, we're going to dive deeper into sequences. So let's go over some important concepts of sequences at the start. And as a note, most of this should be a review from your lesson, so I'm going to quickly go through the important terminology because we're going to use that in the first half of this worksheet. So if we're describing some sequence a sub n, we will use the following terminology. Increasing, meaning that a sub n plus 1 is greater than a sub n. So if we were to write out a sequence, a sub 1, a sub 2, a sub 3, continuing, then we'll have some a sub n. After a sub n comes a sub n plus 1, and that continues on. So when we're talking about increasing, this a sub n plus 1 term is bigger than a sub n. So let's try to make up that follows that rule. So this would be, let's see, if we had -5, 0, 5, 10, 15, and so on. This is a perfect example. This is actually an arithmetic sequence where I'm adding 5 each time. So the term that comes after is always 5 greater. So it is indeed an increasing sequence. Next, we have the term non-decreasing. Now, non-decreasing is if a sub n plus 1 is greater than or equal to a sub n. So the only difference between increasing and non-decreasing is the fact that in non-decreasing, a sub n plus 1 can be equal to a sub n. So up above, this sequence that we already wrote out for increasing is a perfect example of non-decreasing. Each term is greater than or equal to. But let's do an example of a non-increasing sequence that is not increasing. So that would be, let's start at 0. If we went from 0 and we stayed on 0, and then 1, 1, next go to 2, then 3, then 3, and so on. You can see that I'm adding 1 every other time. So I'm starting at 0, continuing to 0. A sub n plus 1 is indeed equal to a sub n. And then right after that, I add 1, and now I'm greater than. And then I'm equal to again, and then I'm greater than after that, and then equal to, greater than, then equal to. So this is a case of non-decreasing. So all increasing sequences are non-decreasing, but not all non-decreasing sequences are increasing. Kind of like that concept of all squares are rectangles, but not all rectangles are squares. So let's now move on to decreasing. And decreasing is exactly what it seems like. Each a sub n plus 1 is now going to be smaller than a sub n. So an example of this would be, well, let's just do the opposite of that increasing. I'm going to start at 15 and then go to 10 and then 5, 0 to -5. Next would be -10 and so on. You can see as my index increases, my value is smaller than that previous. So that's an example of decreasing. And then we also have non-increasing, where a sub n plus 1 is going to be less than or equal to a sub n. So what I'm going to do is take this non-decreasing sequence from up above and flip it into a non-increasing. So I'm going to start at 3, and then go to 2, and then go to 1, and then go to 0, and after that would be -1, then -2, and so on. And just like up above, all decreasing sequences are non-increasing, but not all non-increasing sequences are decreasing. Now the next term we're going to go over is monotonic. And monotonic means essentially that our sequence moves in one direction. So up above, when we're increasing or we're non-decreasing, we're still moving in that same general direction. Or if we're decreasing and non-increasing, we're still moving in that same direction. So numbers 1 through 4 are all monotonic. Now, if a sequence isn't monotonic, we'll think of this as oscillating. An example of an oscillating sequence would be Well, if it's not moving in one direction, it's going to be going back and forth. So if we started with 1 and then went to -1, if we just had those two terms, we would say, oh, this looks like it's going to be decreasing or non-increasing. But let's go back to 1. So from here to here, I'm decreasing, but then from -1 to 1, now I'm increasing. And let's continue this on to get a pattern. We'll go back to -1 and then to 1, and we'll continue on. So because we're neither increasing or decreasing, neither non-decreasing or non-increasing, this is an example of oscillating, so this sequence is not monotonic. It does not only move in one direction. The next few terms we're going to go over are bounded above, bounded below, and in general, bounded. When a sequence is bounded above, that means there's some number that all the terms in my sequence are less than or equal to. So let's represent that number with some variable b. Bounded above means that every a sub n is going to be less than or equal to that number b. And bounded below, we're going to have every single term in our sequence greater than or equal to some number, and we'll make that a capital A. So that means that a sub n is going to be always greater than or equal to a. That's bounded above and bounded below. So overall, if we're bounded, that means we're bounded both above and below. So I'm just going to take a sub n and set it between those two numbers from above. So we're always less than or equal to some b value, and we're always greater than or equal to some a value. Those terms in our sequences are always greater than or equal to one number and less than or equal to some other number. So now that we've covered this terminology, let's go ahead and look at some pictures or some graphs of some sequences and label them accordingly. So let's look at this first one. Let's first focus on the direction it's moving, and then we'll talk about whether it's bounded or not. And I'll go ahead and zoom in right now. So if you notice for this first one, if each of these dots represents the value of our term, and this is as n increases, these terms represent our a sub n, well, a sub n plus 1 is always what compared to a sub n? We're always greater than. So right away, we know that this is indeed increasing. And remember, if it's increasing, that also implies that it's non-decreasing. And the other term we can use to describe this sequence is whether it's monotonic or not monotonic. And in this case, we are indeed monotonic because we're moving in one direction. Now let's talk about the bounds. This sequence is clearly bounded below because there's no term that's less than or equal to that starting value. So we know that this is bounded below. All of my terms are greater than or equal to some value, which it looks like 0 this case. I don't have this labeled, so I don't know the exact number, but it does indeed look like all my terms are greater than or equal to 0. So this is bounded below. So the next question, is it bounded above? If we were to continue this sequence on, our terms would get infinitely bigger. Therefore, this isn't bounded above. So we just have increasing, non-decreasing, monotonic, and bounded below. For this next one, you can see that each term that falls after the other is increasing. Even here, we have a small, tiny increase. So this is indeed increasing. And because it's increasing, we know that that implies that it's non-decreasing. And it's moving in that one direction, so it's monotonic. Now in this case, you can see that we're bounded below, just like in the previous example, and we're also bounded above. You can see that if we continued this sequence on, the change is getting smaller and smaller between my terms. We're approaching some finite number, therefore we're bounded above. These terms are always going to be less than or equal to some number. And if we're bounded both below and above, we are bounded. Now quickly, I want to note I skipped over this one statement up above because I thought we needed to see a picture to really get an idea of it. But if we scroll back up, we have this theorem that says a bounded monotonic sequence converges. So think about it. If we're bounded both above and below, and if we're moving in one direction, regardless of whether we're increasing or regardless of whether we're decreasing, if we're bounded, we're trapped between those two finite numbers, therefore we are going to converge. And you can see that this is a perfect example. Here we have a monotonic sequence that's bounded. This is converging to some finite number. Let's see if we have another example of a bounded monotonic sequence on this worksheet. Here we go, perfect. The very next picture. You can see that the terms are decreasing because each subsequent term is smaller than the previous. So we're going to say decreasing. And because it's decreasing, that implies that it's non-increasing. And either being increasing, decreasing, non-decreasing, or non-increasing means that it is moving in one direction and therefore monotonic. Now you can see that all terms are below that starting value, so this is bounded above, and none of my terms are ever going to go below 0. So this is also bounded below. So if you can envision being bounded above and bounded below, this is going to converge to some finite number because it is indeed bounded and it's monotonic. So once again, that theorem, a bounded monotonic sequence converges. And we can see that from the picture. Scrolling on to the next example, each term that comes after the previous term is either the same or it's greater than. So because it's either the same or greater than, that means that it is, well, it's not increasing every time, but it is indeed non-decreasing. So here's an example of a non-decreasing sequence. And because it's non-decreasing, that means that it's moving in one direction, it's monotonic. And lastly, let's look at whether it's bounded below, above, or both. As we continue on, we would assume that the sequence continues in that same pattern. So we're going towards infinity, so our terms are getting infinitely larger as we continue on, so we're not bounded above. However, we are indeed bounded below because all of our terms are always greater than or equal to 0, therefore we're bounded below. Continuing on to the next example, we're really mixing things up here. If we're looking at this, our first term decreases, but then we increase, and then we decrease again. So we know for a fact we're not strictly non-increasing or non-decreasing, or increasing or decreasing. That means that this is not monotonic. We're not just moving in that one direction. So we're going to label this as oscillating. Next, let's check the bounds. Well, it appears that we continually get larger numbers and we continually get smaller numbers. So we're not bounded above, we're not bounded below. This is just not bounded. And again, let's look, if we think about the next term, we went from this term to one that was down here. Our next term would be all the way up here. The following term would be even lower than the one not previous, but before that. And this will continue to get bigger and bigger, almost like a funnel opening up. Therefore, it's not bounded. And remember, it's not monotonic, so it's oscillating. Next is another example of an oscillating sequence. We decrease, increase, decrease, increase, and so on. Because we're not moving in one direction, this is oscillating. However, as opposed to being not bounded, notice that no terms are ever greater than or equal to where we started, or less than or equal to that second term that appeared. So we are indeed bounded both above and bounded below. And if we're both bounded above and below, that means that we are indeed bounded. So think about this. Here is an oscillating sequence that's bounded, and what does it look like we're going towards? Looks like we're going towards 0. So this is going to indeed converge. However, let's look at this next example. Again, we're oscillating. You can see that we're bounded above and we're bounded below. Therefore, we're overall bounded. However, unlike that previous sequence where we saw that it was converging, this is always going to go from the same positive number back to the same negative number. It's never going towards some finite number. Therefore, in this case, we are not converging. We would have to say that it diverges because we're not approaching some finite number as n goes towards infinity. So just because it's bounded does not mean that it converges. However, if it's monotonic and bounded, then it does converge. Now for this last picture, I just have a graph that's drawn. So I'm going to label a few things on the side and we're going to make it happen. I want something to be, let's say, non-increasing, but not necessarily decreasing, and bounded above. In order to be non-increasing, that means that a sub n plus 1 is always less than or equal to a sub n. But if we're not decreasing, that means that a sub n plus 1 is not strictly less than a sub n. So we're really going to focus on that fact that a sub n plus 1 can be less than or equal to a sub n. So I'm going to start with 2 even values, and then I'll go to some smaller values. Now it's really up to you how you draw this. It doesn't have to be pictured like so, but this is a good example where you can see that I have a term that's equal to and then less than, equal to, then less than, equal to, then less than. This is indeed non-increasing, but it isn't strictly decreasing. And my starting terms, I have nothing that's going to be greater than or equal to those values. Therefore, you can see it is bounded above. So hopefully through those quick examples, you have a better understanding of the terminology behind a sequence. Let's continue on. Remember, I told you back in Calc 1 a while ago to remember the squeeze theorem because it's going to come up again. And I said it's going to come up again with sequences in series. So let's go ahead and take a look at the squeeze theorem with sequences. Now, if you recall the squeeze theorem, our goal was essentially to find two functions where our original function is trapped in between. So if we're talking about sequences and I have some term a sub n, that's that explicit formula from the one sequence, that's always less than or equal to b sub n, and that's always less than some other sequence term c sub n. If I know what happens to this sequence and what happens to this sequence as n approaches infinity, if those are equal, then I will know exactly what happens to that function that's trapped in between. So let's say that the limit of a sub n as n approaches infinity equals L, and let's also say that the limit of c sub n as n approaches infinity equals L. Well, because a sub n approaches L and c sub n approaches some finite number L, that means that because of both of those, the limit of b sub n as n approaches infinity also equals L. And the squeeze theorem is as it says, where this function is being squeezed in between two functions that we know what's happening to them as n increases. So let's go ahead and do this example. We're going to find the limit of the sequence sine of n over 4n squared plus 3. Now, sine of n is a trig function that's trapped between what two values? Well, -1 is always less than or equal to the sine of n, which is always less than or equal to 1. Now, if I divided everything by that same exact denominator, everything will still be balanced. So if I divide this by 4n squared plus 3, you can see here's my original, sine of n over 4n squared plus 3, and then I have 1 over 4n squared plus 3 as well. All I did was divide everything by that same denominator so that I have my original explicit formula. Now, if this is my a sub n and this is my c sub n, I'm going to take the limit of each of those. So the limit of -1 over 4n squared plus 3 as n approaches infinity is going to equal what? As n gets larger, that denominator gets larger, so my overall fraction will get smaller, so this goes towards 0. Now, if I take the limit of 1 over 4n squared plus 3 as n approaches infinity, same deal. I have a constant in my numerator over some denominator that's getting bigger. That means my overall fraction is getting smaller and heading towards 0. So because the limit of a sub n equals the limit of c sub n as n approaches infinity, that means that the limit of my b sub n, my sine of n over 4n squared plus 3, as n approaches infinity, must also equal 0. And just for fun, let's actually look at the picture of this. Let me go ahead and pull up a graphing utility. So the green dots was my c sub n, the purple dots was my a sub n, and my b sub n is trapped in between those two. So as we go closer to infinity, you can see that each are indeed approaching 0. It's trapped in between. And here, just so you can see the shape of this more clearly, I switched my interval up, making my n values go not from whole numbers, but through tenths of decimals, just so we can see how b sub n, that red sequence, is indeed trapped between that green and that purple sequence. And that's the squeeze theorem. Let's move on to the next concept in this example worksheet, growth rates. Now, growth rates are extremely helpful with calculating limits. Specifically, they're really helpful for calculating limits when dealing with rational functions. When we have some function over another function, if we can decide which one's growing faster, that means the overall fraction is going to go towards some infinity if that numerator grows faster, or it's going to go towards 0 if that denominator grows faster. So let's go ahead and list out some functions so we can see which types of functions grow faster. So in the case of growth rates, n is going to be my variable, so I have positive real numbers p, q, r, s, and b is also positive real that's greater than 1. So what I'm going to start with is going to be my ln function. So if I have the ln raised to some positive real number q of n, that is going to grow the slowest of all my functions I'm going to discuss. So what grows faster than the ln of n, all raised to the q, is going to be my variable n raised to some positive real number p. So n to the p is going to always grow faster than ln of n, all raised to the q. And what grows faster than that? That's going to be some n to the p multiplied by the ln of n raised to the power of r. And what grows faster than that will be n to the p plus s. And what's going to grow faster than that will be b to the n. Faster than that is n factorial. And then lastly, growing faster than that will be n raised to the power of n. Now each of these are representing sequences, so I'm going to go ahead and put my sequence brackets around them. So knowing what sequences grow faster than others will really help us when we're finding those limits. So let's use this growth rate of sequences to help us figure out whether the following sequences converge or diverge. So whether they're going towards infinity or whether they're going to go towards some finite value, 0. So we have the ln of n over n to the n. Which grows faster? Well, n to the n grows faster than all my other functions. So because my denominator is growing faster, that means the limit is going to go towards 0. So this converges to 0. Let's look at the next one. N to the n over n factorial. Notice n to the n is growing faster than in factorial. So because my numerator grows faster than my denominator, I'm approaching infinity. Therefore, my sequence diverges. And sorry about that bright light, I think I fixed it. So continuing on, into the fourth over 3 to the n, some positive real number to the n is going to grow faster than some n to a positive real number. So because 3 to the n is going to grow faster than n to the fourth, this limit is going to go towards 0. So this converges to 0. And again, that's because the denominator is growing faster than the numerator. Looking at d, we have n squared minus 99 over the ln of n. N squared is going to grow faster than the ln of n. So regardless of whether I'm subtracting 99, that's just subtracting a constant, which doesn't really dictate the growth of my function. N squared grows faster than ln of n, therefore this diverges. 8 to the n over n factorial, that's like a b to the n over n factorial, and b to the n does not grow as fast as n factorial, so because my denominator is growing faster than my numerator, this converges to 0. N to the 10th over the ln of n, all raised to the power of 1000. Here is my n to the p, there is my ln of n to the q. Doesn't matter that that's raised to the 1000 versus n being raised to the 10. N to some power grows faster than the ln raised to some power, therefore this diverges. N factorial over 14 to the n. N factorial is always growing faster than b to the n, therefore this also diverges because that numerator grows faster. And then 1.1 to the n, so some real number raised to the n, that's a b to the n. And then we have n to the 10th, that would fall before. Therefore, our numerator grows faster, meaning that the overall fraction will diverge. So this sequence diverges as well. So we just did a through h in a matter of a few minutes. Imagine if we were to write out the limit of each and then use L'Hopital's rule when we got infinity over infinity. This would be very tedious to do. However, with growth rates, we did it in a snap. So now that we've discussed growth rates, let's look specifically at this b to the n from up above. Well, remember that b to the n term, if we wrote that in a list, that would give us a geometric sequence, because to get from one term to the next, we're multiplying or dividing by that same number. However, now let's not restrict b to be greater than 1. Let's let b be any value. So as opposed to using b, I'm going to use r. So now we have r to the n. We're going to look at specific r values that make the sequence either converge or diverge. So let's go ahead and draw out a quick number line. So what we're focusing on is the limit of r to the n as n approaches infinity. What exactly is happening? And let's look at some specific values of r. Let's look at when r is -1, 0, and 1. Let's start by looking at when r is equal to 1. When r equals 1, we have 1 to the n, and we're taking the limit as n approaches infinity. 1 raised to any power is always going to be 1. And we don't need to apply L'Hopital's rule here because I'm not taking a function of n that's approaching 1 and then raising it to some n that's infinity. I'm literally taking the constant 1 and raising it to the n as n approaches infinity. That's always going to be 1. So if we're getting 1, that means that the overall sequence, that r to the n, is going to converge to 1. So when we're at 1, we're converging. So I'm going to fill this in, and specifically on this number line, I'm going to find the values when r to the n converges. So we know it does indeed converge when we're at 1. Let's look at for values greater than 1. If we have 2 to the n, 3 to the n, 4 to the n, think about taking the limit of that. That's going to approach infinity. So when I have values greater than 1, I'm diverging. So I'm going to go ahead and shade this area in yellow to represent that I'm diverging. Now let's think about if we had 0. 0 raised to the n as n approaches infinity is always going to be 0. So we're converging for 0 as well. So I'll fill that in as a dot. What happens between 0 and 1? Well, think about if I had r as some fraction between 0 and 1. For example, let's take a look at 1/2. If I was raising this to the n and taking the limit of it, well, distributing my exponent through, 1 to the n is going to be 1 over 2 to the n. Or even if I left this n in my numerator, my denominator is growing faster, which means overall my sequence is approaching 0. Therefore, I'm also converging between 0 and 1, because in order to get a fraction between 0 and 1, that numerator is smaller than the denominator, so when I distribute my exponent through, my denominator is going to grow faster. So as of right now, all of this also converges. Let's look between 0 and -1. Again, I have a fraction where my numerator is smaller than my denominator. So between 0 and -1, my denominator is growing faster than my numerator. So again, my sequence is converging towards 0. So I'm going to fill this in. But let's take a look at what happens when we're at -1. When we're at -1, think about -1 to the n as n approaches infinity. When n is an even power, we're going to get a +1. When n is an odd power, we're going to get a -1. So that sequence is going to go back and forth between -1 and 1, never reaching a finite value. So actually at -1, we're going to diverge. And then if you look at numbers less than -1, like -2, -4, and so on, again, that's going to oscillate, and as opposed to being bounded between -1 and 1, we're oscillating now, but going further apart. So this also diverges when we're less than that -1 value for r. So our geometric sequence r to the n converges specifically when -1 is less than our r value, which is less than or equal to 1. So from -1 all the way up to and including 1, our geometric sequence r to the n will converge. And it diverges when r is less than or equal to -1 or when r is greater than 1. Also, if we want to dive into this even a little more, we can think about when our geometric sequence oscillates versus when it doesn't. When we use positive r values, we're only going to ever get positive outputs. But when we think about those negative r values, when we have a negative r value and we're raising it to a power, depending on whether that is odd or even, will depend on whether our output is positive or negative. So we're actually oscillating for all of this up to 0. Our geometric sequence is oscillating, which I think is something important to try to visualize and understand. And as far as converging goes, we knew that between -1 and 1, we had a fraction where the denominator was greater than that numerator, so the overall fraction was going towards 0, but when we were specifically at 1, our sequence converged to 1. Every other r value that makes the sequence r to the n converge, we converge to 0, with the exception of when r is 1, then we converge to 1. So in example 3, based on this above, let's quickly fill this in. We're going to state whether the following converge or diverge. So think about taking the limit of 2 to the n as n approaches infinity. Well, our r value equals 2, and 2 is greater than or equal to 1. Therefore, this diverges because it doesn't fall within that convergence interval. Looking at b, -3 to the n, our r is equal to -3. Therefore, since again, we're not falling in this convergence interval, -3 would appear somewhere over here, then we are indeed diverging. And think about if I wanted to explain the sequence a little more in depth, what that negative r to the n would look like. would be oscillating, whereas up above in A, it would just be monotonic and increasing. B, we'd be oscillating, but still not bounded. Looking at C, -1/2 to the n, my R value is a -1/2. Because my R is negative, I know this is going to be oscillating. However, because it falls in this interval of when my geometric sequence converges, I know that this converges. So if we think about this, this is actually an oscillating sequence that's bounded both above and below, but it's going towards some finite value, and that value is 0. Now for D, our R value is 5/6. Therefore, again, because 5/6 is between -1 and 1, this converges. And if we were to think about this visually, 5/6 to the end is decreasing and bounded. So because it's decreasing, that implies that it's monotonic, moving in one direction, and a monotonic bounded sequence converges. So just get familiar with throwing that terminology in when talking about sequences. Now I introduced this geometric sequence because understanding this geometric sequence will help when we go and move into a geometric series. It's all about that R value that makes the sequence converge or diverge, and the same thing with a geometric series. It's all about that R value that dictates whether the series converges or diverges. Except with geometric series, because we're summing terms, we're going to get different numbers as opposed to just 0 for converging or just 1. And there's a formula for that that'll help you walk through. So in the next few videos, we're going to dive deeper into series, so sums, no longer lists, but sums, and we're going to also take time to really discuss the geometric series, because that's one series that when it converges, we have a formula for figuring out what it converges to. So until the next video, good luck with your online learning.